To understand the evolution of the universe, we have to study the universe at earlier times. Now, astronomers and cosmologists are lucky because we have time machines. There are two types of time machines we use. The first type of time machine is a telescope. As we look out in space, we're looking back in time. The light from the objects we see deep into space started their journey to us millions or billions of years ago. As we look out in space, we can look back in time and track the evolution of the universe. Another type of telescope we can use is an accelerator, like the Large Hadron Collider. The universe emerged about 14 billion years ago from a hot soup of elementary particles. The accelerator at CERN can recreate the conditions that were present in the primordial soup. So in some sense, the CERN accelerator is a telescope. It allows us to look back in time to a period in the history of the universe when the energies of the particles that were colliding were comparable to the energies colliding at the Large Hadron Collider. One of the great theoretical ideas in cosmology in the last 20 or 30 years has been the idea that early in the history of the universe there was a period of very rapid expansion of the universe known as inflation. A prediction, a consequence of this idea, is that there should be tiny fluctuations in the temperature of the universe as measured by satellites such as Planck. So when Planck looks out in space back in time, they're seeing the temperature differences as existed 380,000 years after the Bang, but they were imprinted on the universe during inflation, well in the first second, the first very small fraction of a second in the history of the universe. But there's another prediction from inflation, that is, there should be a background of gravitational waves produced during inflation. Primordial gravitational waves. Now, there are experiments today looking for gravitational waves, but those involve the gravitational waves produced today in collisions of black holes, in spiral of astronomical objects today. The Planck satellite has the possibility of detecting these primordial gravitational waves. And they would do this by measuring a property of the microwave background known as polarization, which corresponds to a different intensity in the radiation coming to us as a function of direction. In this past year, there's been two remarkable discoveries that bear on the study of the early universe, on cosmology. The first discovery was by the Planck satellite, which has measured tiny fluctuations in the temperature of the universe looking in different directions. The Planck satellite has a telescope that looks out in space back in time to about 380,000 years after the Bang. When the Planck telescope looks out in space and back in time and measures the temperature fluctuations, they are seeing not only the universe as it existed 380,000 years after the Bang, but they see the impact, the signal of events that occurred earlier in the history of the universe that left an imprint in the form of the temperature fluctuations. So in fact, the Planck satellite is looking back to the very early, within the first second of the history of the universe. And these fluctuations, cosmologists believe, came from the action of a scalar field that existed during inflation. Until the last year, we have never discovered a fundamental scalar field. And at CERN, they discovered the Higgs field, which is a fundamental scalar field. So it tells us there may be something right about our ideas of the origin of the fluctuations that were measured by Planck. We're familiar with an electromagnetic field. We may not feel it, but throughout space, there are electromagnetic waves that are coming to us. The electric fields have a different property than the scalar fields. Electric fields have directions associated with them, while a scalar field can be the same, independent of directions, everywhere in space. The Higgs field today, responsible for the symmetry breaking of the electroweak theory, is the same at every point in space. At every point in space, there is a Higgs field of 246 billion electron volts at every point in space. It's the same in all directions. If it would not be the same in all directions, you would have a different weight looking in this direction and looking in that direction. Your weight would change as you look in different directions. The scalar field is the same at all places in space and the same in all directions. The Higgs boson discovered at CERN is an excitation of the scalar field. So the scalar fields are similar to an electric field that might exist in space, but it has different properties with respect to it has no direction and it can be constant everywhere in space.